On our last video with derivatives of trigonometric functions, we spent the time to prove that the derivative of the sine of x was equal to the cosine of x. Now, the derivative of the cosine of x is equal to negative sine of x, and that can be similarly proved the way we did the derivative of the sine of x using the definition of the derivative, the limit as h goes to 0 of f of x plus h minus f of x over h. So that said, we also explored graphically the connection between these two curves, sine of x and cosine of x, as well as cosine of x and negative sine of x. And we can see using our graphical approach for finding derivatives that those two relationships are true as well. So now we just have the other four trig derivatives to look at. So I'm going to go ahead and jump into looking at what is the derivative of the tangent of x, and as well we can do what is the derivative of the secant of x. And then we would have the other two, which again would be good exercises for you to practice. So let's do this one. Let's start with the tangent of x. So if I want to take the derivative of the tangent of x, I can simply look at, since I already know the derivatives of the sine and the cosine of x, I could simply look at the fact that the tangent of x is the sine of x, the ratio of the sine of x over the cosine of x. And that's a quotient. And we know how to take derivatives with the quotient rule. Quotient rule. So let's apply the quotient rule here. So applying the quotient rule, this is going to be equal to whatever the derivative of the sine of x is times the cosine of x. By the way, we know the derivative of the sine of x minus the derivative of the cosine of x. Again, we know that derivative times the sine of x, all divided by the cosine of x quantity squared. Continuing to simplify that, we have not taken the derivatives yet. So before we simplify, let's take the two derivatives. So the derivative of the sine of x is equal to the cosine of x times the cosine of x. And if you feel comfortable enough with the quotient rule, then go ahead and you can jump from here to here. I just wanted to write out those derivative operators one more time here, a couple more times maybe on this video. Then the derivative of the cosine of x is a negative sine of x times the sine of x, all divided by the cosine of x squared. Well, now we get into our simplification, cosine squared of x, and then subtracting a negative sine squared. We're actually adding a sine squared of x over a cosine squared of x. Well, use a little identity here, Pythagorean identity. And we know that the sine squared plus the cosine squared, which is the same as the cosine squared plus the sine squared, is just 1. And that's 1 over the cosine squared of x. But 1 over the cosine is the secant, so this is equivalent to the secant squared of x. And we have just found another trig derivative. We just found the derivative of the tangent of x. So we could add that to our little list up here. So on our list up here, we have the derivative of the sine, the derivative of the cosine. Let's add in the derivative of the tangent of x. And we're just building up a bank of derivatives that we can take, different functions that we're used to, our trig functions. We've talked about exponential functions now and power functions, and we're just building to that bank. We're just putting more and more tools into our toolbox so that we can take derivatives of more and more diverse functions. So the derivative of the tangent of x is the secant squared of x. Okay. Let's do just one more on this video, one more full proof here, and then we'll get into some applications of finding derivatives, of combinations of functions, and looking for horizontal tangent lines and all those good things. Scooch this over just a little bit. There we go. Okay, so let's take the derivative of the secant. And in a really similar way to how I took the derivative of the tangent, I'm going to start by just thinking about, well, how can we express the secant? Or can I express the secant in terms of the functions that I already know the derivatives of? And of course the answer is yes, because the secant is 1 over the cosine. So I could just simply start by saying this is the derivative of 1 over the cosine of x. And again, this is a quotient. And so again, I can use the quotient rule to take this derivative. So this is the quotient. I can take the quotient. This is a quotient, so I can take the derivative of this function by utilizing my quotient rule. And this is going to be, again, the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And then I'm going to divide by the denominator, the quantity cosine of x squared, all of cosine of x squared. So then taking the derivative, I get 0 times the cosine of x minus the derivative of the cosine of x is a negative sine of x times 1 all over the cosine of x squared. Well, of course, this term is 0, and then we're subtracting a negative, so that's a plus. So we end up with simply the sine of x over the cosine of x squared. Right? Now, that is our answer. We have found the derivative. But to simplify this a little bit, I notice that I have a sine of x, and then I have in the numerator, and then I have cosine of x times cosine of x in the denominator. So if I actually think of that like 1 times the sine of x what I could do, just scooch that apart a little bit more. Kind of wonky parentheses there, but you get the idea. 1 over the cosine of x is the secant of x, and sine over the cosine of x is the tangent of x. And we do prefer to write it that way. So the derivative of the secant of x turns out is, technically, I guess you could look at this version right above, but we prefer when we write it to write this version. It's the secant of x times the tangent of x. And that has given us one more. So we've proven that the derivative of the tangent of x is the secant squared. We've proven that the derivative of the secant of x is secant times the tangent. Let's add that one into our list. And then we would just have to do the last two, but I'm going to go ahead and leave those as an exercise for you to practice. They're similar to what we just did for the tangent and for the secant. So looking at the cotangent, obviously that's cosine of x over the sine of x. So similar to the tangent. And the cosecant is 1 over the sine, so similar to the secant, which is 1 over the cosine. So the derivative of the secant of x is the secant of x times the tangent of x, and we just proved that. Okay, so that said, we could go through and we could prove the other two, but I'm going to go ahead and just project them up here on the next screen, and then we're going to utilize all 6 of those derivatives to take some derivatives of some combinations of functions with functions that we've looked at before, products and quotient rules, exponentials, and power functions. All right, so here are the 6 trig functions derivatives. So the derivative of all 6 trig functions is right here on the screen. So make sure that you write this down, commit this to memory. This is, again, the 6 trig functions we are going to use from here on out, and we've got to know their derivatives because they are going to show up and we're going to need to use them. Similar to knowing trig functions identities, the basic identities. We need to know the basic identities and the relationships between these 6 trig functions. And now we also need to know not just their relationships to each other, but their relationships to their rates of changes, so their derivatives. So here they are. So here are the 6 trig functions derivatives. Again, screenshot and commit these to memory. We will need to know these. So let's go ahead and do some examples. All right, so let's take a look. So I just copied that derivatives of the 6 trig functions. So we have them for reference here until we have them committed to memory. And let's go for it. Let's just jump in here and start taking derivatives. So we need to take the derivative of these 2 functions. One of them is a product rule and one of them is a quotient rule. So clearly this is a product rule on our first one, 5x cubed being the first function, f, and cosine of x being g. So we're going to utilize our product rule. And so just as a reminder, because we're going to start to speed up our work just a little bit here. So product rule is if we're taking a product of if we have a product f times g and we're taking the derivative, so the derivative of a product is f prime times g plus g prime times f. And so our f is 5x cubed and our g is the cosine of x. So rather than writing the derivative operators in here, I'm going to just jump right to it. So the derivative of 5x cubed is 15x squared times cosine of x. But then I have to add the derivative of g of x times f of x, so g prime. So the derivative of the cosine is the negative sine of x times f of x, 5x cubed. And now I have my derivative. So I jumped right into it. I didn't write the derivative operators on this one, just utilizing my product rule and going right for it. So here is my f prime times g plus my g prime times f. And now all I'm going to do here is simplify just a little bit, not much to do really. I do see that I could pull out a 5x squared, and maybe that makes things a little bit nicer. And so doing that, I then end up with 3 cosine of x, at least gives it to us in factored form, minus x sine of x. And there's my answer. So my derivative, there's a nice bit of a simplified answer. So there is the derivative of y. There we go. All right, let's do another one. Now let's do this one. So doing this guy, this e to the x tangent of x, is going to utilize the quotient rule. So the quotient rule for this one, we are going to have to use our quotient rule, and our quotient rule says that if you have f over g prime, that's f prime times g minus g prime times f all over g squared. All right, so utilizing that, we're going to get in here and take this derivative, because this is our f and this is our g. So f prime of x is equal to the derivative of f. E to the x is just e to the x. The derivative of e to the x is just e to the x. So that's just going to become e to the x times the tangent of x minus the derivative of the tangent of x, and we just proved that that was actually equal to the secant squared of x times f of x, so times e to the x all over the tangent squared of x. And here, let's see, is there much we could do here? We could pull out, we obviously have that e to the x in the top, so we could pull that out, leaving me with a tangent of x minus a secant squared of x over a tangent squared of x. Now, if we wanted to, we could continue and we could simplify. I'm going to go ahead and just leave it here. I'm looking at that secant squared and knowing I have an identity that connects secant squared and tangent squared. So maybe if we wanted it all in terms of tangent, we could do that. But I'm going to just leave it at this, and we can spend more time on simplification on the applications, on the ones where we need things like the horizontal tangent lines or equations of tangent lines.
For this next example, it makes more sense here to actually simplify a little bit before we get going on the derivative. Because if I were to go for the derivative right now, I've got both a product rule and a quotient rule. And sometimes we have to just deal with that. But in this particular case, I'm looking at that cosecant of x and I'm thinking, you know, I know that the cosecant of x is the same as 1 over the sine of x. And look at what happens when I do that. I now have two fractions with the same denominator, and so my function that I can start with before taking the derivative, e to the x minus x over the sine of x. And now I just have to apply the quotient rule. So just remembering quotient rule, f prime g minus g prime f all over g squared. So we'll get in here and we'll get going. So the derivative of g is going to be the derivative of the numerator. And I'll write out the derivative operator again on this one. Just as we're getting practice, again, this is not necessary to write out the derivative operators, but I want to continue to practice just remembering that quotient rule all over sine squared of x. And then the actual derivative when we apply our derivative operator here becomes e to the x minus 1 times the sine of x minus the cosine of x, because the derivative of the sine is cosine, times e to the x minus x all over sine squared of x. Now, in terms of simplification, we could distribute and see how things go here. I'm not sure we're going to get a whole lot of simplification here, but let's see. So e to the x sine of x minus the sine of x minus e to the x cosine of x minus x cosine of x. And I don't see any common factors or any obvious simplifications here, so we will call this good. And there's our derivative. But again, it made a little more sense on this particular one to simplify first. Okay. Let's do another one. Now, on this function, we actually have a product of three functions. We've got x, sine of x, and cosine of x. So what I'm going to end up having to do is apply the product rule twice. And so how does that look? I know we just have to decide in our first application which is f and g. And then within f and g, we're going to have to, again, apply the product rule because each of these is a function. So as we go through this and we apply the product rule, again, f prime g plus g prime f. When we apply the product rule, we'll have to remember that when we take the derivative of f, it itself is a product. And so we'll apply the product rule twice there. And then derivative of the cosine of x times x sine of x. So now when I take this derivative, I have to remember that this is also a product. And so taking the derivative of x sine of x itself is going to be a product rule. And here we're going to go right to the product rule. So the derivative of x is 1 times the sine of x plus the derivative of the sine of x, which is the cosine of x, times x. All of that times the cosine of x. So remembering from here to here, I had to again apply the product rule. All right, and then the derivative of the cosine of x is negative sine of x times x sine of x. And let's just see, as we go through here, how does this work out? If we do some distribution, we'll get the sine of x times the cosine of x plus the cosine squared of x, and we have an x on that term. Minus x sine squared of x. And this time I do actually see something kind of fun that we could work with, because right here, oh, well, not too fun, but we could, I actually thought that might have been a plus, but it was a minus. So we could pull an x out. We've got a common factor of x on that particular term. So we could pull out, we could pull the x out, and that would give me x times cosine squared of x minus sine squared of x. If that had been a plus, that would just be 1. It's not, but we could apply a different identity. This piece right here, trig identity, is simply the cosine of 2x. And, you know, as we start to work more and more, and after this section we will work more and more with trig functions, we do want to recognize those identities and write this as x cosine of 2x. I'll box both of these in. Both of these would be acceptable answers for our derivative. Put a little or right here. Both of these would be acceptable answers for our derivative, but it is nice to recognize that identity popping out there, that double angle identity for the cosine. Okay, let's look at a couple more examples. We're on a roll. So let's do an example with a function that has trig functions in it, and where we have to take it and use the derivative to find some information out about the curve. So for this one, let's find the equation of the tangent line. So we're looking for the equation of a tangent line to a curve at the point pi. Okay, so again, finding tangent lines, we have to start by finding the slope of the tangent line. And to do that, we need y prime, or dy dx. Right? The slope of a tangent line to a curve is going to be the value of the derivative at that point. So let's do it. We got to get in here. We got to look at our e to the x sine of x, and our function. Let's just rewrite our function down here. If our function is y equals e to the x sine of x, then e to the x is our f in a product rule, and sine of x is our g in the product rule. So f times g prime f prime g plus g prime f. And let's go for it. So dy dx. And this time I'm not going to write in the derivative operators. I'm just going to go for the derivative. So the derivative of e to the x is e to the x. The derivative, or the then multiplied by sine of x. So that's just sine of x. Plus the derivative of the sine of x, which is the cosine of x, times e to the x. So I'm just jumping right into it. Here's my f prime g plus g prime f. Oh, you know what? There is a common factor of e to the x. Let's pull that out. So the derivative, simplified a little bit, is e to the x times the sine of x plus the cosine of x. All right, so now if we want the actual slope of the tangent line at a point, in this particular case at x equals pi, now we're going to actually find the slope. So let's take this, and now let's look at the slope at x equals pi. So the slope at x equals pi would be dy dx evaluated at x equals pi. And so we're going to plug that in. So that's going to be e to the pi had to move that down underneath so we have a little more space. So that's going to be e to the pi. So when we plug in pi here, e to the pi times the sine of pi plus the cosine of pi. And the sine of pi is, of course, 0, and the cosine of pi is -1. So we end up with negative e to the pi. All right, so that's our slope. So remember, slope of the tangent line is the value of the derivative evaluated at that point that we're looking at. So now we've got the slope of the tangent line. Now all we have to do is write the actual equation. So we were going through x equals pi, and we did not have the y value, so we got to find the y value. So we know that at the point we are at pi, and if I were to plug pi into this function up here, so plugging in pi right here, we would get e to the pi times the sine of pi, but the sine of pi is 0, so that's actually equal to 0. So it's going to be at the point pi 0, finding the ordered pair, and now all I have to do is write the equation. So let's go ahead and use point slope form. So y minus 0 equals negative e to the pi times x minus pi. And that's just going to be y equals negative e to the pi times x plus pi times e to the pi. And we want our answers exact. We don't want to approximate here. We have the ability to find the answers exact. I never had to pull out a calculator to do this problem, and I don't want to. I want these exact answers in their exact form. And there's our slope of our tangent line to that curve, e to the x sine of x, at x equals pi. Let's ask one follow-up question to this particular problem. Let's ask, when would this function have horizontal tangent lines? So let's call this part A, and let's do part B. And let's say, when would at what x values, of x does y equals e to the x sine of x have horizontal tangent lines? Since we already have the derivative, this is now just an exercise in determining when the derivative is equal to 0. So we already know that dy dx is equal to e to the x sine of x plus cosine of x. So we already know that. So let's figure out at what point would that derivative be equal to 0, because that's what it means to have a horizontal tangent line. So horizontal tangent lines occur when dy dx is equal to, or the derivative is equal to 0. So horizontal tangent lines when dy dx equals 0. So let's figure out when would that occur. So when does the derivative equal 0? So when would e to the x times the sine of x plus the cosine of x actually be equal to 0? Well, it's a product, so this is going to happen when e to the x equals 0 and when the sine of x plus the cosine of x equals 0. Well, e to the x is an exponential function, and an exponential function is always greater than 0. So e to the x is always greater than 0, so there are no values here, okay? So this is never going to happen. If you want a visual, think about an exponential function. Exponential functions look like that, right? This exponential function, e to the x, looks like that. So it's never equal to 0, okay? So e to the x is never equal to 0, okay? So it's never. Another way to say that would be never. It's never equal to 0 because it's always greater than 0. Okay, so let's focus in on this part. So sine of x plus cosine of x, well, let's subtract cosine of x. So the sine of x equals negative cosine of x. And then to work with this, I'm looking at this and I'm thinking, well, if I divide by the cosine of x right now, solving trig equations now, I find that the tangent of x is equal to negative 1. Well, when would the tangent of x be equal to negative 1? Well, that happens when x is equal to, and we do always use radian measure, so that's when x is equal to negative pi over 4. So do use radian measure. And include all values unless a restriction on the domain is given. So always use radian measurement for angles. In this class, we will always use, unless for some reason, that less than 1% chance that you're going to be asked for something in degrees. We do always want radian measure in calculus. So we'll use radian measure, so negative pi over 4. So this occurs at negative pi over 4. And then the period of the tangent is pi. So this is going to happen every time we cycle back through a cycle of the tangents period. So this is going to be pi times k, where k is an integer. That little k is an element of the integers. So my notation here, element of. I know we've seen this before, but just as a reminder, integer. It's the set of integers. All right. So it actually is going to have an infinite number of horizontal tangents occurring every time we hit negative pi over 4 plus pi k. What was that original function? Okay, so let's do one more example. Where is this particular function? So another example of horizontal tangent lines. Let's do this one. Where does g of x equal to this time a quotient, cosine of x over 2 plus sine of x? So we've got a quotient rule here we're going to have to apply. So f over g. When find all the x values where our tangent lines are horizontal. So again, if we want to find horizontal tangent lines, the first thing we have to do is find the derivative. So to find those horizontal tangent lines, anytime we're talking about slopes of tangent lines, we got to start with the derivative. And then if we want the horizontal tangent lines, we set the derivative equal to 0. So we're going to be using our quotient rule here. And so our quotient rule, f over g prime f prime g minus g prime f all over g squared. And our f and our g are right here. Here's f, and here's g. So let's get in and do this quotient rule. So our quotient rule, our derivative is going to be equal to the derivative of the cosine of x, which is minus sine of x, times 2 plus the sine of x, minus the derivative of 2 plus the sine of x, so that's actually going to be 0 plus, I'll write that, 0 plus cosine of x, obviously that's just the cosine of x, times the cosine of x. And all of that is going to be divided by 2 plus the sine of x squared. All right, and then continuing now just to simplify before we set this equal to 0, get this as simplified as we can. So let's go ahead and distribute out that negative sign. So we have negative 2 sine of x minus the sine squared of x. This is obviously just the cosine of x, so that's minus cosine squared of x, all over 2 plus the sine of x quantity squared. And then I notice in here, I see that sine squared. You know, every time I see a sine squared and a cosine squared together, I think about what I could do there, and I see that they both have a negative. So what we could do right now is we could actually just pull it. Actually, this guy has a negative too. So let's pull a negative out of all of it. So let's pull a negative out of the whole numerator. We have 2 times the sine of x plus the sine squared of x plus the cosine squared of x, all divided by 2. Let's zoom in just a little bit. 2 plus the sine of x squared. But then, of course, this piece right in here is that Pythagorean identity. That's just 1. So this is actually, my derivative ends up just being negative 1 times 2. That worked out really nice. 2 sine of x plus 1 divided by 2 plus the sine of x quantity squared. Now we're looking for those horizontal tangent lines still, so we want to set this equal to 0. So we're going to set this equal to 0. And when would this be equal to 0? Well, when we have a ratio like this equaling 0, the only way that can be 0 is if the numerator is 0. You could also see that by multiplying both sides by the denominator. But we could also just think about, well, when is a ratio going to be 0? When the numerator, when you have a over b equals 0. That's going to happen when a equals 0, when the numerator equals 0. Okay, so it's kind of a little sidebar right there. All right, let's jump in there and set that numerator equal to 0 and do a little bit of trig here. So when this is going to happen when 2, technically there is that negative 1 there. Let's write it 2. Negative 1 times 2, I jumped ahead of myself there. 2 sine of x plus 1 equals 0. Divide off the negative 1, so when does the 2 sine of x plus 1 equals 0, and that's going to happen when the sine of x equals negative 1/2. And so then thinking about, well, when does the sine of x equal 1/2? And again, using radian measure, this is going to happen when x is at negative, x is the angle negative pi over 6. But it's also going to happen an infinite number of times every time the sine of x cycles through its period. So it happens at negative pi over 6, and then every 2 pi k after that, where k is an integer. And there's our answer. So it's going to happen at all of those angles. And we'll zoom out so we have the whole thing here. So that is when that function has horizontal tangent lines.